Well, welcome everybody. Today, Thursday, the 1st of June, 2023. Welcome to established gas members, near and far. I think we've got one a bit further than the home counties. Old and new members and our visitors, and especially to our speaker, Professor Karen Aplin. Most of us have felt awe and wonder when experiencing the majesty of a thunderstorm. Lightning displays are spectacular, potential hazards, and they affect atmospheric chemistry. It is associated with specific types of cloud and meteorological processes, as well as being implicated in the origins of life on Earth. However, there is more to atmospheric electricity than just lightning. Its quieter and less well-known sibling exists in every planetary atmosphere as a continual flow of ions and electrons, and can form a global-scale electrical circuit with lightning acting as a battery. The iconic Voyager 1 mission was the first to photograph an extraterrestrial thunderstorm at Jupiter in 1979. Since then, lightning has been detected on most other solar system planets. On Earth, small currents away from thunderstorms can affect clouds, interact with particles from dust or pollution, and even potentially influence the weather. Similar non-thunderstorm processes may also act in other planetary atmospheres, such as Titan and Venus. In this lecture, Karen will provide the unifying scientific background and context for the study of atmospheric electricity and describe past, present, and future observations. Karen Aplin is Professor of Space Science and Technology at Bristol University and visiting professor at the University of Reading's Department of Meteorology. She previously worked at the University of Oxford's Department of Physics and the Space Science and Technology Department of the Rutherford Appleton Laboratory. Her research program seeks to understand and exploit electrical properties of atmospheres through novel instrumentation and experiments. She also works on space weather, dust, and volcanic ash charging, and recovery of historical electrostatic data. Her first degree was in physics and philosophy at Durham University, followed by a PhD in experimental atmospheric physics at the Department of Meteorology, University of Reading. She also has a classical performance diploma from Trinity College of Music. She was the recipient of the Royal Astronomical Society's James Dungy Lecture in 2021. Karen, the floor is yours.
Thank you very much. Let me just sort out sharing my screen. That working?
And you're mute at the moment, I'm afraid, and that may be our fault.
I'm not muted. Can you hear me?
I know.
Yes, on Zoom.
How's that working?
It was all right.
Is that okay?
Yes.
Yeah, okay, I'll carry on.
Yes, that's good.
Good, okay. Yeah, thank you very much for the invite to speak to you today. I'm going to share some of my work on electricity in other planetary atmospheres, as you heard. So the structure of the talk, I'll give a little introduction, and then I'll talk about lightning in other planetary atmospheres, and then sort of the, as I said in the intro, like the less exciting sibling, but still quite important. There are electrical processes going on away from thunderstorms in atmospheres. which I'll tell you about. And then they can get kind of joined up by this concept of a planetary electric circuit. So I will touch on that as well, and then I'll try and bring it all together at the end. Because this talk skips around quite a lot of planets and concepts, I shall attempt to use symbols to indicate what I'm on about. So if I'm talking about lightning, I'll try and have a little lightning cartoon, and then the non-thunderstorm type of atmospheric electricity with a cloud, and the global circuits with a battery. Although, yeah, I hope I remember to put them on all the slides, but hopefully that will sort of keep you where I am, what I'm talking about, if it's not clear, if I'm jumping around topics a lot. So the kind of one slide summary of this talk is that there's lightning has been detected on quite a few planets, Earth, Jupiter, Saturn, Neptune, and Uranus. And slightly controversially, it may or may not have been detected on Venus. I'll touch on that later. And also Mars is in there because Mars is a bit different. We expect Mars to have lightning, but we haven't seen it yet. But kind of the whole point of this talk, cosmic rays and other ionization processes, which I'll talk about. So away from lightning, you have this other stuff going on, which releases charge, which is electricity in all atmospheres. So that's really the one slide summary. So if you've got a short attention span, that's it. You can leave now. So all atmospheres are electric. That's the talk, and now I'm going to expand on that for the next 45 minutes or something. So the intro, so the basic sort of principle and the approach I've taken is that the laws of physics are the same everywhere, which shouldn't be a surprise to an astronomy society. And that means you can use the same scientific principles to underpin atmospheric electricity wherever you are. The same things happen. That means there are a few things. It means you can use terrestrial analogies to understand what's going on at the planets, which can be easier because it's easier to look at lightning on Earth than it is to look at lightning on another planet. And you can use quite similar instrumentation to measure atmospheric electricity wherever you are. And also you can test space instruments in Earth's atmosphere if you choose your environment carefully to make it like the environment you're interested in. So a desert, if you want a dusty environment, you could go to a desert. If you want to have a low pressure, you can go to a high altitude, and so on. So this is the approach that we take throughout the talk. And what the sort of specific thing I brought to it, I think in particular, is bringing together different communities of researchers from terrestrial atmospheric science and also astronomy, planetary science, and so on. I think when I started working on this topic, those people didn't really talk to each other very much, and now I think they do more. So as you'll have heard, I did my PhD in an atmospheric science department. So I measured atmospheric electricity in Earth's atmosphere, but I've always been interested in space and so on. And then I started applying it to other space environments. And there was this whole community of people who'd done similar things for other planets, but the Earth people didn't know about them. And that didn't seem a very useful way to use resource at a time when space missions are really still, they're getting easier to do, but they're still very difficult and very expensive, especially to other planets. So this idea of joining up the Earth and planetary science way of thinking about it and getting the people to talk to each other to move the subject forward is sort of the approach I've taken. So now I'm going to talk about lightning. What is lightning? Lightning is a big spark. And on Earth, we see lightning in thunderclouds and in volcanoes. And we know that lightning's been around for a really long time, sort of because we have this fossilized lightning, fulgurite, which is when lightning strikes sand, it's very hot, so it kind of fuses to sand. You get a nice channel. That's a famous picture of a fulgurite from the 1960s, but you can see them in Arran. If you go to Arran, there are some in the rocks there, and they're lovely. So we know lightning's been around a long time. It's been around almost as long as Earth's atmosphere. And how do we get lightning? Well, typically in a thundercloud, you have ice and snow and water and soft hail, which is called graupel. And you have a lot of convection, you have a lot of mixing and sort of upwelling of air. And so you start off with a cloud with some rain in it, and then it grows and becomes colder. The higher up you go, and then you have this hail and snow. And because there's a lot of mixing of particles, they collide with each other, and when they collide, they transfer charge. Typically, very typically, because it's a very variable process, the ice crystals will acquire a positive charge and sort of waft up to the top of the cloud because they can move more easily in the air, and the hail particles will fall down. And that means you get a separation of charge in the cloud. And when this gets a big enough separation of charge, it exceeds what we call the breakdown voltage of the air, and you get a spark. And that's what lightning is. So you can have all sorts of different lightning. So what does lightning need? It needs convection, which to create the thundercloud, and separation of charge to build up the voltage. You can't have lightning without both those going on. And there are various different types of lightning. You can have lightning like from a cloud to ground, which is of course what you've all seen. You can also have lightning inside a cloud. You can sometimes see that sort of a flickering light inside clouds. That's called intra-cloud lightning. You can have cloud to ground, and also there's a newish, relatively recently discovered type of cloud, which is lightning going up from the clouds. That's much harder to see with the naked eye, but there are photographs, and I think I've got one a bit later. Yeah, so here are some pictures of the lightning. I'll start with, hopefully you can see my mouse on the right hand side. I'll start with the right hand picture because I was just talking about sprites. This right hand picture has two types of lightning in it, as well, maybe several. Thundercloud lightning. I can't tell whether that's in the cloud or going to ground. It looks like it's a mixture of both, actually. And then right up here, we have a sprite, a red sprite, which is a different type of lightning going up from the top of the thundercloud to the top of the atmosphere. So that's one type of lightning. They're called transient luminous events. And here's sort of cloud to ground lightning, I think. This is a video taken by one of my friends. No, that's not cloud to ground. Yes, that one was cloud to ground, inside the cloud and cloud to ground. And slightly rarer is volcanic lightning. This is when you have a volcanic eruption. It's a similar sort of mechanism. The volcano spews out a lot of ash, and this charges up. And sometimes it can mix with a thundercloud, and then you get a mixture of ash and ice and so on, and it sort of enhances the charging. So you can see lightning in volcanic plumes, which is quite cool. I've never seen it myself. I'd very much like to. And you can have lightning at the bottom of the plume. Let's quit that. Which can be caused by sort of breakup of rocks, creating charge as well as the convection mechanism that I mentioned just now. So those are types of lightning exemplified by Earth. So lightning, I've shown you pretty pictures. It's nice to look at them, but why is lightning important? It is important. Firstly, it's a hazard in space. Well, it's also a hazard on Earth. I'll focus on space. Clearly, people can get struck by lightning. Objects can get struck by lightning. In space, you can have your spacecraft or its solar panels being struck by lightning. This could be problematic. You can have charged dust, which is a sort of precursor to lightning in some environments, sticking to solar panels and causing power problems. Clearly, if it's a crewed mission, there's a hazard to the crew from lightning. And then moving on to chemistry and life. There's a famous experiment done by Miller and Urey in the 1950s. And they got a tank and they had some amino acids in it, such as you might, no, sorry, they didn't, they had some gases in it, such as you might find at the beginning of Earth's atmosphere. And they sort of applied sparks to this tank. I think they did it for about a year. And after that time, they went into the tank and they found there were amino acids in there, which are the building blocks of life. So there's this argument that lightning might spark life. And there's a picture of Stanley Miller. I think Miller was a student in the 1950s. This is a picture of him more recently, perhaps looking a bit sick of the attention his work's got, but it's very famous. Lightning fixes nitrogen on Earth. And also in other environments, lightning can contribute to chemistry. So it can ionize gases, and then you can have acceleration of electrons in the electric fields associated with lightning, which can sort of like act as a catalyst to create different chemicals on Mars. So there's sort of chemical effects of lightning as well as the electrical effects. Lightning also, this might sound obvious, but it indicates severe weather, and it indicates that you have a thundercloud. You have dust or water ice clouds, and this means if you see lightning, you can be fairly clear that there's convection going on, and this can be used as an indicator to signal atmospheric dynamics, which is what's done for Jupiter and Saturn now. So how do we detect lightning? We all know about the flash of light from lightning. That's caused by optical emission from a very hot lightning channel. And what you find is that the gases in the atmosphere, they will typically emit a particular wavelengths of light when excited. And if you have a lightning detector on a spacecraft, it will look at a particular portion of this light to avoid other things that could cause the signal. Terrestrial lightning excites nitrogen because nitrogen's the main gas in Earth's atmosphere. But as you know, there's also oxygen. And we actually use this oxygen line at 777.4 nanometers, which is a good emission to use. And there have been predicted, I should say, there since about 95, there have been satellite observations of lightning in Earth's atmosphere. And so we actually detected lightning in Jupiter's atmosphere, for example, from a spacecraft before we detected it in Earth's atmosphere with a spacecraft. Now NASA have had two types of lightning detector, and they can have very detailed maps now of averages of lightning over Earth. And in other planetary environments, you can predict what wavelength the lightning will excite based on lab experiments. I thought it'd be fun to look at the colors of these lights. So actually for terrestrial planets, so for Earth and Venus and Mars, we expect to look at this oxygen line, and it's actually almost in the infrared. It's quite a dark red color. For the gas giant planets, which have hydrogen and helium atmospheres, we expect to see the 656 nanometer, much brighter red light. So those are the lightning detection wavelengths that would be used or are used for some filters already, and would be used if you're going to have a lightning camera with a filter at the gas giant planets. You can also detect radio signatures of lightning. That's because the ionized channel, the current's been flowing, acts as an antenna, and this emits radio waves, and you get variations from planet to planet. And if the lightning is in a sort of smaller scale, it emits at a higher frequency, the longer channels, and the propagation distance is also related to frequency. So you get a variation in the sort of radio spectrum of lightning, depending on the characteristics of the lightning. And here you can see a graph of the radio emission expected from Saturn lightning and Uranus lightning. And one of the things to note is it's very faint. So Janskis are a very tiny unit, mainly used in radio astronomy. So one Jansky is 10 to the -6 watts, minus 26 watts per square meter per hertz. And you can see Saturn lightning. So Saturn lightning has actually been detected from Earth with a radio telescope. And Uranus lightning, not yet. It's fainter. So that is quite a challenge, particularly if you consider the effect of the ionosphere of the planet, which is an ionized layer at the top of the atmosphere, which affects the remote sensing possibility. So that affects what can get out of a planetary atmosphere in terms of radio frequencies. And it also, Earth's ionosphere, also radio noise, also affects what you can measure from Earth. So if you were to look at this from Earth, you wouldn't see very much at all, because radio emissions within Earth's atmosphere dominate massively. So this Earth detection of Saturn and Uranus lightning, they have to pretty much look at these frequencies to see anything. But obviously, if you're in space, you don't have to worry about Earth's atmosphere, so that makes it a little bit easier. Another type of radio signature from lightning is, which you might be less familiar with, is called a Schumann resonance, which is an excitation caused by lightning between the surface and the ionosphere within an atmosphere. And that's very low frequencies, just a few hertz. So this could be a different way to detect planetary lightning, although it's probably easiest to do from within that planetary atmosphere, from in situ detection rather than remotely, because I'm not sure much of the signal would get out of the ionosphere of the planet. Other signatures of lightning include magnetic signals, because of course all radio waves, EM waves, are also magnetic signals, and whistlers are signals from lightning that go along the magnetic field lines around the planet, and they can be detected by magnetometers. And I have here a clip of a whistler, an audio clip. Let's see if it works.
Earth whistlers.
So you can see why they're called whistlers. This was a really old detection from an early spacecraft launched by the University of Iowa, doing radio detection of lightning in Earth orbit. No, not again. And finally, we can acoustically detect lightning through a pressure wave, which is, of course, thunder, and that's formed by heating of the air in the lightning channel. This is only detectable relatively near to the storm, and clearly it only works in the atmosphere you're interested in, because you have to have air to have thunder, to have sound. You might be surprised to learn that there is a thing called a thunder day on Earth, which is still the official way of recording lightning from the ground. So if you have a weather station, they have observers at them. If they hear thunder one day, they make a note, and that's called a thunder day. And that is how we do global lightning detection on Earth still, without the help of satellites. So it sounds terribly old-fashioned, but it's still very much used for Earth. If you were going to consider thunder on other planets, the sound propagation depends on the atmospheric properties. So it's expected to be quite good sound propagation on Titan and less good on Mars. And in fact, the Huygens probe that landed on Titan in 2005 had a microphone, which was supposed to look, well, would have looked for thunder. It didn't hear any. And I think one of the Venera missions to Venus also had a microphone, which again didn't hear any thunder, but they were hoping to. So just to summarize how you detect planetary lightning. So there are these different types of signal that are emitted by lightning: optical, electromagnetic, radio, and radio waves mainly, and acoustic detection. And if you have an Earth-based attempt to detect them, the easiest way to do that is probably to use a telescope. If it's near enough, you can look at the night side to improve the contrast. You have a filter to look in these wavelengths. Or you can use a radio telescope, which has been pretty successful, actually. If you have a spacecraft that's detecting planetary lightning, you can use a camera, again, with or without a filter. And again, it's easy to look at the dark side of the planet and look at the lightning contrast. And you can do radio detection or magnetic detection from a spacecraft. If you're actually in the planet's atmosphere, if you've got a lander or a probe, you can obviously look for transient flashes from lightning and these other options of looking for the Schumann resonance. You can also look for local electric field changes, which are from lightning, and you could even have your microphone, as I've suggested. So those are the different approaches that are used to detect lightning on other planets. Now we'll go on and look at some examples. You might want to think about what constitutes a lightning detection. That's not always straightforward. People do argue over what actually counts as a detection. I think probably if you have a couple of these at once simultaneously, that is okay, but people do disagree over what a lightning detection is. For example, for Venus, that's quite controversial. So the first extraterrestrial lightning detection was at Jupiter in Voyager 1. And here is the picture on the right-hand side, and they saw these flashes, which are lightning, and they also saw aurora, which was also the first detection of aurora, another planet, I think. And the whistlers also detected by Voyager 1, as I played you the recording of earlier. And just to note, the Juno mission's been at Jupiter, NASA Juno mission recently. And their star tracker, so a star tracker is a kind of engineering camera that the spacecraft has to keep for navigation by the stars. So that's a kind of low-grade camera in comparison to the very nice sort of atmospheric cameras they're using. But this was just an engineering camera, detected this lightning in the aurora in 2018. So you can see how much the technology has come on in 40 years. That was like the best camera on Voyager 1. And this is just the engineering one on Juno, and it still takes very nice pictures of the aurora and lightning. Some radio signals from lightning might not get out on Jupiter, sorry. That's something a little bit strange about its characteristics that mean it's not as easy to detect radio emissions from lightning as you might expect, even though the lightning on Jupiter is very powerful. Definitely is much more energetic than terrestrial lightning. And where does the lightning come from on Jupiter? It comes from weather and clouds, thunderclouds, pretty much like Earth. So it has a mixture of clouds, has some made of ammonia and some made of water and ice, which are deep in Jupiter's atmosphere. And it has very active weather. And you can see from this is a good picture from Juno with its science cameras. You can see all these swirls and eddies. They indicate there's a lot of weather, a lot of dynamics on Jupiter. And we assume that lightning on Jupiter comes from the areas where the water ice clouds, the observations seem to be consistent with that. So it's sort of been assumed that the Jupiter lightning comes from the same mechanism as Earth lightning. However, very recently, there's been a new type of lightning detected on Jupiter, which is what they call shallow lightning, which is much higher up, nearer the spacecraft. And it is thought to be caused by a different mechanism, which is ammonia and water. And instead of hail, they've got what they call mushballs. This is very exciting because I think it's the first type of lightning we've seen in the solar system, which is caused by a mechanism we don't really have on Earth. Previously, it's all about dust clouds and water ice clouds. And the mechanism's roughly similar to Earth. So they have this big water cloud on Jupiter, but then up the top, it has this ammonia layer, and you get a mixture of ice and ammonia, which they've got as green in this diagram. And you get a kind of cycle of the mushballs rising and falling, and a sort of growing melting cycle and evaporation. And this acts to transfer charge in a similar way to the soft hail and ice charge transfer that I talked about earlier for Earth. So that's what they think is happening on Jupiter, and that's really, really new and a big finding in planetary atmospheric electricity. And yeah, so lightning's been observed by loads of spacecraft. I think every spacecraft pointed at Jupiter since Voyager 1 has seen lightning. It's really common and it's really powerful. So they now use it as an indicator of convection. They just use it to see what's going on with the weather, and they know that there are updrafts where they see lightning, and that helps atmospheric dynamicists to understand the weather on Jupiter. Moving out now to Saturn. Cassini spacecraft detected a lot of radio emissions from lightning on Saturn, and they were also photographed at the same time. So that was really the sort of unambiguous detection that people are hoping for. And you can see that there's this big long-lived electrical storm. They're very long-lived. They last for like a year, our time. And some of these storms were even detected on Earth. So you had a radio detection on Earth, a photograph and radio detection of the planet that all matched up in terms of time. And that's very impressive. The storms on Saturn live near the equator and around 35 degrees, and amateur astronomers have had a really good contribution to understanding Saturn's lightning. So if you're looking for an opportunity to sort of make a contribution to the scientific community, turning your telescope at Saturn, if you can do that, would be great. So the radio emissions, the lightning emissions are very strong, much stronger than terrestrial storms, but overall they're weaker than Jupiter's lightning. So they've got very powerful lightning, but not as powerful as Jupiter. And just for scale, the storms on Saturn are the same size as Earth itself. So it's a sort of similar to Jupiter lightning, but not quite as powerful. On Mars, we have a slightly different type of lightning, and we expect to have a slightly different type of lightning in the dust. So Mars is quite windy. That's because it hasn't got much atmosphere, and that means the surface gets heated up quite efficiently by the sun, and that causes temperature differences around the planet, and that causes wind, causes air to flow from one area of the planet to another. This lifts up loose material and blows it up, and you get dust storms, which can cover the whole planet. And this GIF here on the left, that shows Mars without a dust storm, and on the right it shows it with a dust storm. So they get really big and they really obscure the whole planet. And we also have dust devils on Mars, which are quite regular, just like they're pretty much the same as ones on Earth. You might have seen videos of them. And the dust in the dust devils and dust storms becomes charged, and that's basically a sort of rubbing process called triboelectricity. It's a similar process. If you rub a balloon on your jumper or something like that, you can get enough charge on the balloon to stick it to the wall, that kind of thing. Is that sort of charging mechanism. So that's what's expected to happen on Mars. Here's a picture of a dust devil whizzing across Mars's surface. So why do we expect to see lightning? We know this dust is charged. We know dust devils on Earth are charged, and the Mars ones are very similar, so we expect them to be charged too. And dust devils on Earth don't make lightning. And that's because the breakdown voltage on Earth, the voltage at which you need to have to build up to get lightning, is much bigger for Earth than it is on Mars. In Mars, the air pressure is quite low, and this means the breakdown voltage is quite low, and that means it's kind of easier to get lightning in the Martian atmosphere. So if you had the same dust devil on Earth, you wouldn't expect to see lightning, but if you transported it to Mars, the same size and all that, you would see lightning, almost certainly. So that's why we expect to see lightning. Also, there are lab experiments charging up dust in carbon dioxide tanks, low pressure, to copy the Martian atmosphere, and we see discharges then. And also some models predict lightning. So yeah, so why don't we see the lightning then? Well, I think this is probably because The lightning is expected to be relatively small scale within the dust clouds. You're going to have sort of patches of positive and negative charge, and relatively weak, relatively small lightning, such as the picture on the bottom right there, which shows a little glow at the bottom. That's an artist's impression of a discharge on Mars, corona discharge, glow type discharge. So they're expected to be weak. Obviously, it's very dusty, and that means this blocks the light, so it's going to be hard to see. Also, we don't really see radio emissions from lightning. People have looked for them, but they haven't seen them, both by spacecraft at Mars and by radio telescopes on Earth. There's a few things, but it's not really settled that it's been seen. And that's probably, again, because it's quite a weak signal. So the sort of evidence we have for charged dust on Mars is that it sticks to stuff. This is quite an old picture of some dust stuck to a rover wheel. That doesn't kind of fall off, it stays there, and that's because it's charged. And there are some more recent pictures of it stuck to solar panels, but that is evidence that the dust is charged. So if we want to know more, I think the thing to do would be to go to Mars and put a lightning detector on an instrument, on a spacecraft. And of course, this has been attempted, but unfortunately, every mission that's had an atmospheric electricity instrument has failed, because Mars is quite a hard planet to get to, and it's been very unlucky. And the most recent lander that failed was this Schiaparelli lander, which had this micro Aries sensor, which was a lightning and general atmospheric electricity sensor, and that crashed. So far, no luck. Now, the ExoMars mission does carry some relevant instrumentation. There's various magnetometers and electric field sensors on the MEGRE instrument, which would be capable of detecting lightning. And there's also something called a dust suite, which include a sensor to measure the charge on dust. Unfortunately, however, this was on the Russian part of the instrument. And so when Russia invaded Ukraine, it was cancelled. So that is also not going anywhere. It's due to be launched last year, but it's not happened, disappointingly. So at the moment, I mean, we're doing some work at Bristol. We're looking for magnetic signals from charged dust to support future missions, having previously done some electrical measurements of charged dust in the lab. And my student, David, has designed this rig. And we have a sort of rig in which we are dropping dust and also rotating dust, trying to loft it. And we're going to measure, well, we can measure electric fields with a remote electric field sensor here, and a sort of plate that detects the dust when it lands on it, and also looking at magnetic measurements. There is a lander called InSight on Mars at the moment that is really more of a sort of geology, seismology mission, but it has a magnetic field sensor on it as well, and it has had some dust devils go over it, so we're also looking at that. So at the moment, it's all about lab and Earth-based measurements of Martian lightning. There won't be any in situ measurements for a while, sadly. Now, could Venus have lightning? Despite this lovely artist's impression, I think it wouldn't have that sort of lightning. Many observations have been attempted of Venus lightning, both from space and from Earth. And there were some sort of suggestive observations from the Venera probes in the 1980s, and more recently, the Venus Express spacecraft didn't have a lightning sensor with a light detector or electric field detector or radio sensor, but it did have a whistler. It was able to detect things that they interpreted as being like whistlers, but there's some debate about how that data is interpreted. Also, other spacecraft that have successfully detected lightning at Jupiter and Saturn did flybys of Venus, and they didn't see any lightning, even though we know that lightning sensors work, because they worked to detect lightning at Saturn and Jupiter. So that's all a bit up in the air at the moment. Another question is, how would you even have lightning on Venus? Because the clouds aren't made of water, they don't have ice in them, they're made of sulfuric acid droplets. So the mechanism is very unclear for how that would work. Yeah. And as you might know, the air pressure sort of near the surface of Venus is incredibly high. I think it's about 100 times higher than it is on Earth. And that means probably the breakdown voltage, which increases with pressure, is incredibly high. And that probably means you can't get lightning near the ground on Venus, which is why I think that little video is incorrect, even though it's quite a nice video to have. So attempts to understand Venus lightnings is very much an ongoing research topic at the moment. So as I said, there's no evidence for ice in the Venus clouds, there's no known mechanism. And additionally, the clouds appear, modeling studies suggest the clouds actually conduct electricity quite well. And this is not so good for lightning, because you have to have this separation of charge within a cloud, positives and negatives, to get lightning. And if the cloud conducts electricity well, the charges just equilibrate, they just flow away. So this suggests, again, that we don't know how lightning would happen on Venus if it does. And so, as I've said, we have to figure out where the lightning might occur. A cloud to ground seems impossible for reasons I've suggested. There is some work suggesting that there are sprites, that there are upper atmosphere, that there could be upper atmosphere lightning, which might be easier to detect from orbit. So these are lab suggestions of what Venus sprites might look like in a mixture of gases that is similar to the upper atmosphere of Venus. You might be able to see these because Venus has this very thick cloud layer, but these would be above the cloud, so they might be easier to detect from a spacecraft. And there's also the possibility of volcanic lightning, because we know there have been volcanoes on Venus in the past. There's a spacecraft, a Japanese spacecraft at Venus at the moment called Akatsuki, and it has a lightning camera on it. And so far it has seen one flash, which is here. And there is some, it's not properly published yet. There's some debate about whether this is really a lightning flash or whether it could have been something like a meteorite. So Venus lightning has many questions, very, very unknown, although I think it's an active research topic. Moving out to the ice giant planets, Voyager 2 is the only spacecraft to have been to these planets, and it detected radio signals from both Uranus and Neptune. There was no optical detection of lightning. There were cameras, we've seen their lovely pictures. I remember seeing them when I was a kid, and they really, really got me into space science and things when I was a child. And there were these radio signals, which were called UEDs, Uranus electrostatic discharges, and something similar from Neptune, they were more like whistlers at Neptune. So the radio emission was actually stronger from Uranus than it was from Neptune, for reasons that are not known. Both these planets have deep water clouds, so it's sort of assumed that there could be lightning, and it would be from the deep water clouds, much like on Jupiter and on Earth. And it's quite powerful lightning, certainly on Uranus, to get out and be detected. On Neptune is a lot weaker. We don't understand why these are different. In fact, Neptune's known to have an internal heat source. It has some heat source inside it that causes convection, causes upwelling, which is what Jupiter also has. So if you were just looking at it on paper, as it were, you might expect Neptune to have the stronger lightning than Uranus, but that's not the way it was seen by Voyager 2. Uranus is also a promising candidate for ground-based lightning detection, and there's a radio telescope that was looking for Uranus lightning from the ground, and they did do some searches. However, it is in eastern Ukraine near Kharkiv, and I'm not sure if it's still there anymore. I don't know, which is a very sad story. So I fear there's not going to be a great deal of work on that in the near future. That it would be great to detect that from the ground with a suitable radio telescope. So to summarize this part of the talk about planetary lightning detection, so what's been seen and tried and what hasn't been seen, so sort of moving outward. Venus not confirmed. There have been a lot of attempts to see it on various different missions, from Earth, from space, and in the atmosphere, but nothing conclusive. With Mars, it's also not conclusive. Well, there's probably more marginal evidence, really not detection, I think, from these radio data and the Mars Express. And there's still no in situ instrumentation that is relevant, unfortunately. It looks like there won't be for a while. Jupiter, lots of detections from many spacecraft and from the Galileo probe in the 90s. And with Saturn, much the same, and it's got this radio detection from Earth. Titan is Saturn's largest moon. It has a very sort of extensive semi-Earth-like atmosphere, and people have tried to look for lightning there with the Huygens probe and other instruments, and it's not being detected there. And for Uranus and Neptune, it looks like it has been detected, but there's no optical detection, and they've attempted to see it from Earth, for Uranus, but that's not successful yet. So there's a lot of lightning around the solar system, but there's still quite a lot that's not understood. Now I'm just going to move on to the next part of the talk. This is about the other type of electricity that I mentioned in atmospheres. This is from ionization. So even when you don't have thunderstorms, you have electricity in atmospheres. And that's because of these particles called galactic cosmic rays, which are very energetic particles created by astrophysical events such as supernovae, and mainly helium nuclei. There can be other things as well. And what happens is they come into an atmosphere and then they collide with some gas molecule and they make a kind of cascade of particles that comes down to the ground. Well, on Earth, it comes down to the ground. And then you have this maximum sort of halfway up the atmosphere, which is this sort of balance where there gets to be enough atmosphere for most of the particles to decay, and then you have a lot of secondary particles. And many of these particles ionize the air. So they break down the air molecules into ions and electrons, and that is electricity. So that's what the fundamental of this part of the talk is about. So all atmospheres have cosmic rays in them. They get everywhere. They're very energetic. They can get a long way into atmospheres. Depending on the environment, you also have other sources of ionization. On Earth, most of the ionization near the surface comes from radioactivity from rocks, and so this might be expected in other planetary environments. You can also have UV, solar UV, ionizing gases. On Earth, we don't get that so much because we have an ozone layer that protects us from solar UV in the lower atmosphere. Also, space weather events can chuck out a lot of ionizing radiation. These are only occasional, but they can sometimes have an effect. And that's clearly only really relevant for the terrestrial planets, probably Venus, Earth, and Mars. The others are a bit too far away to be significantly affected by space weather events. So yeah, as I said, ionization makes ions and electrons. Sometimes, depending on the chemistry of the atmosphere, these prefer to make cluster ions. So if let's say you have a nitrogen molecule that might be ionized into N2+ and an electron, you might just get those like kicking around on their own. But depending on the chemistry, sometimes you get other molecules which stick to the ion electron and make a cluster, which is a bit bigger, but is still charged. These make the air conduct electricity a little bit, and the conductivity increases with height because there are more cosmic rays the further up you are. So these are everywhere in atmospheres. So what does charge do? Despite the fact they're sort of not that spectacular and they're quite quiet, they can have quite a range of effects. They can make particles grow, which is they sort of enhance growth, which can ultimately help form clouds by several different mechanisms. You can have effects, interactions of these charged particles with bigger particles to sort of remove them. And you can have sort of chemistry effects and some infrared absorption from cluster ions from the bending and stretching of the molecules in those ions. At places like Earth, where we have quite active weather, these ionization effects are really small. If you go further out in the solar system, there's less weather really, because there's less solar radiation. And this means there's a much greater role for these small charge effects. And that's what we see. So for example, when Voyager 2 went to Neptune, it took some pictures of Triton, its largest moon, and it saw some very thin ice clouds, which were not expected. And somebody had to try and explain how they were there. And one suggestion was it was an ion-induced effect, or one suggestion, in fact, the only suggestion. These very thin sort of cirrus-like clouds, I believe, are made of nitrogen ice. And that's just thought to be due to ionization rather than any weather type effects, if you like, such as we see on Earth. How do we look for these effects in planetary atmospheres? Well, one of the ways, obviously it's hard because they're subtle effects. We have to sort of look for them indirectly. And one way to do that is knowing that cosmic rays are affected by the sun's magnetic field. The sun has an 11-year cycle. Many of you will know about this already, sunspots and things coming and going on, and solar emissions on an 11-year cycle. And when the sun's more active, its magnetic field is stronger, and this deflects cosmic rays away from the solar system. So all cosmic ray traces have a 11-year cycle in them. And we can use that to search for ionization effects in things like clouds in planetary atmosphere. So that's the sort of approach that's been taken to look for ionization in many atmospheres. I've jumped the gun slightly. That's this 11-year stuff, you do that when you can't do in situ measurements, but there have been one set of in situ atmospheric electricity measurements made by the Huygens probe that went to Titan. And it had two types of instruments that measure air conductivity, something called a relaxation probe, which is a sort of probe that you put a voltage on, and then the voltage decays related to the amount of electricity that's in the air. And there's something called a mutual impedance probe, which is similar. And the pictures of them are shown here. And so I was saying that you can use common instruments. You can use a relaxation probe in Earth's atmosphere to measure the same thing. In fact, part of my PhD was doing that for Earth's atmosphere. And so they were quite interested to see if there were thunderstorms on Titan as well. And they had particle detectors and a microphone. They didn't see any thunder or lightning. They did get some atmospheric electricity results. However, it was a bit more complicated than they thought, because there were aerosol particles, sort of cloud-like particles kicking around, and also electrons and ions. So there's a lot of data analysis that needed, and it's still going on actually. But roughly speaking, the profile of conductivity that I mentioned and that I showed on the earlier slide has this sort of peak in the middle part of the atmosphere. Looking outward to Neptune, it was suggested many years ago that clouds of methane particles are actually formed by ion production on Neptune. And this was, so here are the ions produced by cosmic rays. These are the ions we expect to see on Neptune, and then they react with the gases, the methane and hydrogen in the atmosphere, to make these clusters, and this makes clouds. And this is exactly the same mechanism as you see in a cloud chamber on Earth. And here's a picture of a cloud chamber. So there's a radioactive, I don't think there's a radioactive source in this one. This is kind of natural ionization from cosmic rays, and the tracks have little clouds around them from condensation onto the ions. So the cosmic ray comes in, I'll play it again, it makes a track of ionization, a weak track, and then that causes the formation of droplets. It's actually impossible in Earth's atmosphere naturally, but because all planets are different, you can get this mechanism happening on Neptune. And it actually contributes to an 11-year solar cycle in Neptune's clouds, which was observed for a long time with a telescope from Earth. And we also see something similar in Uranus's atmosphere. This is work that I did, some of the work I'm proudest of that I've done actually. And it's the first evidence that you can get similar effects in two planetary atmospheres when they're sort of magnetically connected to the sun, and the cosmic rays cause clouds in both these atmospheres of Neptune and Uranus. So I said I was going to talk about this idea of a global circuit. Now, what is that? This is an idea that you can combine, brings together thunderstorms and ionization. The idea is that the thunderstorms here act as a kind of battery that charge up the upper atmosphere, and that you get a current flow of these ions that are away from thunderclouds that I was talking about earlier, and they drift. So you get a voltage from the top of the atmosphere to the bottom, and that causes a current flow. So the current is driven of ions is driven through the atmosphere from the top to the bottom. This was first proposed for Earth by C.G.R. Wilson, who's actually invented the cloud chamber. I should have mentioned him earlier. He's very famous to particle physicists because he invented the cloud chamber, which was the first way you could visualize the first sort of instrument of particle physics, if you like. But he's actually obsessed with clouds and weather, and that's why he invented the cloud chamber. So in atmospheric electricity, we very much like C.G.R. Wilson, and he also proposed this idea of a global circuit in the 1920s. It's been around just under 100 years. And somebody proposed that these global circuit idea for another planet could also exist, for Mars, in the 1990s in an undergraduate dissertation. I also did my undergraduate dissertation in the 1990s, but unfortunately that was not me. Mine was much less good. So here's C.G.R. Wilson, and in atmospheric electricity, we like him, and he has a posthumous Twitter page from which he likes to tweet about lightning and related stuff. So if you're interested, do follow him. There's also a mailing list. We have a C.G.R. Wilson Institute for Atmospheric Electricity. We have a mailing list. We have events and talks and things. So if you're interested, you can sign up for that. So what do global circuits do? They provide a direct link between the top and bottom of an atmosphere. So this ionosphere, top, the conductive region, and the bottom, they provide a coupling mechanism through the atmosphere. So that's one thing. The other thing is, because you have a kind of organized flow of ions, then this may have small effects on the radiative balance of the planet, the weather. And so if you have layer clouds, for example, you get current flowing through and it kind of builds up on the edge of the clouds. And this is being observed on Earth. So these are the sorts of effects we expect to happen. And then this affects things like the lifetime of the clouds, the propensity of the cloud droplets to grow, and possibility of rain. Obviously, we've done a lot more on this for Earth than we have for other planets, but we expect this to happen on other planets where there are global circuits. What do you need to have a global electric circuit, thinking sort of general terms? So you have to have these conductive layers. You have to have a relatively conductive surface, and you have to have an ionosphere, an upper atmosphere. This is a layer mainly made of electrons created by UV ionization, typically. And you have to have some ionization. But as I said earlier, ionization is everywhere. So you always have the middle one of those bullet points. And you need some sort of convection, some weather, to separate the charges, to cause this charging up. Typically, this would be lightning, but it doesn't have to be lightning. It could be another type of charge separation. So we can go on and think about, could we have a global circuit on Mars, for example? And this would be driven by dust, because as I said, the lightning on Mars is driven by dust, which we strongly expect to be there. And you can apply this idea. So you have this charging, and then you have a current flow around the planet so you have, in all global circuits, the thunderstorm, whatever you want to call them, storm regions act as the areas that charge up the circuit, but then it exists everywhere. So you have a voltage in the atmosphere everywhere, even away from the storm. So outside, on what we call a fair weather day, away from sort of local sources of charging, then you would have about 100 volts per meter on Earth. So if you could measure that now, I mean, it's been a nice day here. I don't know what it's been like in Surrey. Nice clear day. We would expect to see that voltage outside today. And it would be the same on Mars. You would expect to see a voltage, electric field in the atmosphere. So we could think, could Jupiter have a global circuit? We know it's got lots of lightning. We know it's got ions and electrons. We know it's got an ionosphere. Actually, this all gets a bit more complicated because the lower layer and the gas giant planet the surface isn't really a well-defined thing. I mean, I think people think it has this rocky iron core very deep inside, surrounded by a layer of very high pressure hydrogen, which becomes like a metal. So it is conducting. It's thought to be a conductor because it's under such high pressure that it conducts. But actually, I think this is so deep that the ions wouldn't kind of make it down to the surface, because the cosmic ray muons, which cause most of the ionization, would run out of energy. Even they would run out of energy, even though they've got a lot of energy. So that probably means you can't have this flow from the top to the bottom of the conducting layers in Jupiter, and that therefore there's no global circuit on gas giant planets. So you wouldn't expect to have this organized current flow, even though you do have a lot of lightning. Titan, pretty interesting. Had a lot of surprises. And it turned out to be much more complicated than expected electrically. And then the Cassini instrument, this is some colleagues at Mullard Space Science Lab, actually, which I was talking to the organizer about earlier. They found that there are a lot of charged particles in the upper atmosphere, and they make this haze that makes Titan's atmosphere very, very yellowy, orangey constantly. And is there lightning on Titan, or another way to charge up a global circuit? Well, as I've said, lightning wasn't detected. There was a low frequency signal, which could be indicative of Schumann resonance, this low frequency lightning excitation. And it was found by the Huygens probe. But actually, some years of analysis later, they think it's probably not that. It's probably due to some complicated interaction with Saturn, its sort of parent planet that it orbits. So there is probably no lightning, but there is rain on Titan. I think that's reasonably well accepted in the scientific community. It's not made of water, it's made of liquid methane and ethane. And the rain actually will become charged because there are electrons in the atmosphere, and that will just stick to the raindrops, and the rain will collect electrons as it falls and become charged. So we could start to build up a picture of what a global circuit might be like on Titan, what the atmospheric electricity might be like. So we have UV radiation ionizing the atmosphere and causing an ionosphere. We also have cosmic rays, and there's a bit of natural radioactivity, and there's electrons from Saturn, which complicate matters because it's near Titan. And then you get this ionization, which is the process that happens in all planetary atmospheres. And then you have this strange situation, which is unique, where you have this charge charged cloud aerosols settling, causing the orange color, and they're constantly sinking through the atmosphere. There's a lot of settling. This has been deduced and observed from data from Cassini and from Huygens. And there are convective clouds. They've been observed. So there is convection and rain, but there's probably no lightning. So there's this idea that we may have a global circuit on Titan without lightning and with the convective clouds just acting to charge up the circuit. And there's also this layer cloud and the charging of cloud drops and drizzle. So there's a whole lot going on. So this is a very elaborate and interesting electrical environment. It's likely the electrical, we don't know very much about it yet, but it's likely the electrical properties are very important. In fact, they have been shown to be very important for this haze, but how this interacts with everything else is not yet known. So that everything would become, all the rain and particles would become negatively charged with the electrons there. So this is a topic that's been researched and based on data analysis from the previous space missions. So just moving on to the final section. So electrical discharges, lightning is quite common, and it's been detected actually the majority of planets with atmospheres in the solar system. But there's only really very conclusive detection, optical detection at Earth, Jupiter and Saturn. And there's this non-thunderstorm electricity, which is present in all planetary atmospheres, but the sort of radiative effects, the weather effects of charged particles are relatively more important at the outer planets. And there's this idea of a global circuit that joins up the discharges and the electricity, the current flow, and that can be applied to the terrestrial planets, Mars and Titan, and possibly also Venus, which I didn't talk about really in the talk. The gas giant planets at first sight might have this global circuit, but because they've got many of the ingredients, but due to the lack of a surface that can be accessed by the charged particles, there's no global circuit on these planets, almost certainly as we know it. So we can bring together the phenomena that we see, the atmospheric electricity phenomena at these different planets. And you can see, so lightning, the black line indicates conclusive lightning, and the grey line indicates the grey bolt indicates a maybe. And the same for the sort of weather effects of charged particles. So they're definitely there at Titan, Uranus and Neptune, but things like Earth and perhaps Venus, they're very much under debate. And the global circuits as well, Venus, Earth and Mars, maybe Titan, but probably not these other planets which don't have a well-defined surface. I need to mention exoplanets really quickly, because I'm sure someone asked me about it otherwise. There's a whole world of exoplanets. I try and check the number before I give a talk, because it goes up every time. I haven't checked it today. I think last time I checked for a lecture earlier this year, it was like 5,000. Many have got clouds. It's very likely some will have lightning, and we can use solar system sort of analogies again to estimate the flash densities. And there's this whole different families of exoplanets, like gas giant ones and sort of rocky ones and super Earths. And of course, they're all going to have cosmic ray ionization. And some of my colleagues have predicted that there might be lightning that's quite energetic in some of these planets. However, detecting it seems very difficult. I mean, even though it's powerful lightning, it have to be really powerful to be detectable from one of these spacecraft. If you had a really sensitive radio detector, it might be possible, but I think most of the exoplanet missions are more about photographs, so I'm not sure, but there might be the possibility of lightning detection. There are so many exoplanets, there's so much variety, maybe there'll be one that has strong enough lightning to be detected in due course. So what's happening in the future? I hope I've highlighted some of the sort of open questions, and there are some missions coming up. NASA is going back to Titan with its Dragonfly sort of remote helicopter type thing, and that will have some instruments that are slightly relevant to atmospheric electricity that certainly be helpful, though there are no actual atmospheric electricity detectors. And similarly, European Space Agency is going to Venus, the Envision, and that will have some instruments that should be able to detect lightning in some way, although there's not an actual lightning, not a dedicated lightning detection instrument. So in the absence of space missions, we're getting on with our theory and modeling and our lab measurements, things like what's going on Venus and what's going on in the ice giants, and then lab work is something. So Venus cloud droplet measurements and the Mars analog experiments that I mentioned earlier. So there's a push at the moment to have a new mission to the ice giants. There may be a NASA mission. I think there's a launch opportunity to Uranus in about 10 or 15 years time, and that would be a possibility. So I think there's some work happening on that, and that would be very exciting to have some more measurements of anything really at the ice giant planets, but obviously from my point of view of atmospheric electricity. So to summarize, electricity has been really fundamental part of Earth's atmosphere for as long as we've known about Earth's atmosphere, and it's been measured for a few centuries on Earth, other than the Fulgurites. The measurements started in sort of 1600s. Electricity in planetary atmospheres is much more recent. It's been explored in about the last 40 years, and it also seems as if it's a fundamental part of many atmospheres. So I think we can say that electricity is a really key property of an atmosphere. It's a unifying concept, bringing together many parts of the atmosphere, many areas of scientific research, and it may also even link to the origin of life. So yeah, and there was an advertising hoarding near my house a while ago that had a lightning on Mars theme, which was great. So that's the end of the talk. I'd just like to acknowledge very many colleagues and funders, and I have some books on these topics if you're interested, which the most recent one is this bottom one here. And yeah, you can join the mailing list for atmospheric electricity if you're interested. But yeah, that's the end of the talk. Thank you.
Thank you very much indeed. More than a wrong, but it was very, very interesting indeed. Covered a whole host of issues. Do we have questions either from the floor or the chat?
Could you talk a little bit more about the cause of the sprites and when sprites have been observed on any other planets?
Can I talk more about sprites and observations on other planets? That's the question. Yeah, they've not yet been. I think there was one detection from Jupiter. There's sort of a bit might be a sprite, if I remember correctly. I think it was about the same time as that mushball paper I talked about from Juno. I think there was one other paper about a possible detection. It was a bit cautious. I think it might have been with that engineering camera again. So it wasn't, you know, they sort of saw some weird signals and they hypothesized that it could be that. So not conclusively, and it's not been seen at any other environments. Yeah, it's the same thing. It's caused by an electrical breakdown between, it's normally between the top of the cloud where there's charge sitting and the top of the atmosphere, which is electrons, the ionosphere, and then you get this weak discharge, but it's very kind of big in comparison to thunderclouds. A thundercloud maybe is about 30 kilometers high maximum. And then the ionosphere is more like 100 kilometers. So these sprites, there's a whole family of them. There are many different types, but they go, you know, so they're going from the top of the cloud at 30 up to 100. So they're very sort of diffuse, and they look different because the gas composition of the atmosphere is different up there. It's I can't remember. You see different colors from excitations of nitrogen and things. There's red sprites, blue jets. There's something called ELVES, which is an acronym. So there's a whole weird little family of transient luminous events that we know most about for Earth. And then there are just lab experiments where people have tried to predict them for other planets. I think they're expected to be there on other planets, but not really been seen yet.
Questions? Anybody watching by Zoom? I think we're flummoxed. Karen, thank you very much. That was very clear, very interesting, and grateful thanks for your contribution.
Thank you. I hope you enjoyed it.